I will hand over to Ivan for the actual talk. So Ivan Medennikov is a leading researcher at STC Innovation Ltd. In St. Petersburg, Russia. He completed his PhD degree at St. Petersburg State University in 2016. His research focused on the various aspects of automatic speech recognition, primarily in far-field conditions. He is leading a team of 6 researchers at STC Innovations and supervising 2 PhD students at the ITMO University. Ivan's team achieved 3rd place in the Chime 5 challenge, 1st place in the Voice from Distance challenge, and the 1st place in the 2nd track of Chime 6 challenge. He is also the author of Target-Speaker Voice Activity Detection Approach, solving the diarization system in the Chime 6 dinner party scenario. Cool, so now I'm going to hand over to Ivan, and let's welcome him. Yeah. Okay.
Okay. Hello, everyone. Can you hear me?
Yep, good.
Yeah, we can hear you.
Okay. Thank you for the introduction. And it's a great honor for me to give a talk to this audience. Okay, here is an outline of my talk. I will briefly introduce Chime 6 challenge and in particular diarization problem in Chime 6. We'll consider conventional clustering-based diarization approach as well as alternative approaches. And I will tell about our novel target speaker voice activity detection approach evolution in Chime 6. And in the last part of my talk, we will discuss TSVAD perspectives and limitations and so on. But first, I would like to introduce my company. Speech Technology Center, or STC, is a global developer of intelligent speech and facial technologies with main office located in St. Petersburg, Russia. We are for 30 years in business, and our products are used in 70 countries. We have more than 650 people, regular staff, and more than 100 employees in R&D department. We publish a lot of papers every year. And also we have an international research laboratory at ITMO University, St. Petersburg, Russia. And everyone can try our technologies at our cloud platform website. Our main research directions are automatic speech recognition, voice and face biometrics, speech synthesis, natural language processing, and acoustic event detection. And we participate in many international research challenges, and we take leading positions in these challenges. Our ASR team contains 3 research groups and 1 production group, in total of 26 people. We make ASR for Russian, English, Spanish, Kazakh, Turkish, Arabic languages. I'm leading one of these research groups, which focuses on robust far-field ASR. And note that my group had absolutely no background in speaker diarization before Chime 6, so it was a kind of a fresh look at the speaker diarization problem. Chime 6 challenge data are real conversations of 4 speakers in a dinner party scenario recorded on 6 4-microphone Kinect arrays. There are 22-hour sessions, 16 for training, 2 for development, and 2 for evaluation. The task of the first track is recognition of segmented speech. It's the same as for previous Chime 5 challenge. And the second track's task is recognition of raw multi-speaker recordings. This task was much more difficult and much more interesting for us. You can find more details about Chime 6 challenge on the website. Here are the results of our team in both tracks of the challenge. In the first track, we took 3rd place, and in the second track, we took 1st place, outperforming other systems by a large margin. And moreover, this result, 45%, is close to our results in the first track. And this is because we were able to get a good diarization, which allowed us to apply guided source separation speech enhancement. And after that, we just used our set of acoustic models from the first track system. You can find more details on our CHIME6 system in our system description paper and in our presentation video from the CHIME workshop. But today's talk is focused on speaker diarization problem in CHIME6. Okay, diarization problem in CHIME6 is very hard. This is because of a small amount of training data, only 40 hours, a small number of speakers, only 32. It's a conversational speech recorded in real noisy environments in far-field microphones, but the most challenging feature is a large amount of overlapping speech. This table presents overlapping speech statistics, and as you can see, overlapping speech takes about 20% of total recordings duration. And this makes the diarization problem extremely hard. The most widely used diarization approach is based on clustering of speaker embeddings. And the CHIME6 baseline was based on this approach. It consists of the following stages. First, detect speech regions using speech activity detector. Then split this speech segments by short 1.5 second pieces with 0.75 second step. Compute X vector embeddings for these pieces, then compute PLDA scores, and apply agglomerative hierarchical clustering to divide these segments to 4 classes. And after that, combine successive segments corresponding to one speaker together. And in this table, you can see baseline results. Diarization error rate is higher than 60%, and Jakarta error rate is higher than 70% here. And this is clearly not what we usually call a good diarization. We tried to improve clustering-based diarization in 2 ways. First, we replaced standard X vectors with an advanced 34-layer wide residual network X vectors, which we took from our voice biometrics team colleagues. And second, we replaced agglomerative hierarchical clustering on PLDA scores by spectral clustering on cosine similarities. In this table, you can see improvement from each of these steps. This only spectral clustering without new X vectors, this new X vectors, but agglomerative hierarchical clustering, and finally both of these improvements. And this result is already much better than the baseline, but unfortunately it's not good enough for applying guided source separation. And the main drawback of clustering-based diarization is that it can't deal with overlapping speech because it detects only one speaker at any time. And even a perfect clustering-based diarization system will give diarization error rate more than 20% due to speaker miss errors. And the other drawback is that this pipeline consists of separately optimized blocks. So we considered 2 alternative ways. The first one is a recently proposed end-to-end neural diarization, and the second one is a group of approaches focusing on target speaker speech extraction, namely personal VAD, target speaker ASR, speaker beam, voice filter. Let me first introduce end-to-end neural diarization. This model directly outputs joint speech activities of all speakers, and it naturally handles speaker overlaps. BLSTM or self-attention neural network computes frame-wise posteriors, and after that, permutation-free binary cross-entropy loss is computed. We used open source implementation available at this site, and I'd like to thank the authors for this implementation. But unfortunately, we were not able to achieve impressive results with END in CHIME. And this is probably because this approach requires a lot of training data, but we were allowed to use only a small amount of in-domain training data, and mismatching voxel training data. And also, END processes audio by a few minute-long chunks, and this block-wise processing induces the between-block speaker permutation problem. But this problem can be solved by applying some clustering. We tried k-means clustering on top of wide residual network X vectors, and this worked pretty well. In this table, you can see our final performance with EEND, and it's comparable with the best clustering-based system, but this is still not enough. So let's move to the second group of approaches, target speaker speech extraction. The main problem here is that these approaches require acoustic footprint of a target speaker, for example, I vector. But it's not clear how to estimate this acoustic footprint on noisy overlapping speech. So we decided to start with estimating speaker features on the oracle segmentation. But note that this segmentation is not truly oracle because it contains a lot of silence frames. So it was necessary to exclude these frames from speaker features estimation. For the simplicity of our experiments, we used I vector speaker embeddings and the first channel of the reference Kinect device. Here is a scheme of personal VAD approach. It computes log-mail filter bank acoustic features and combines with D vector speaker embeddings and feed these features to a two-layer BLSTM network. And output here is a three-layer classification layer with outputs three probabilities, namely silence, target speaker speech, and non-target speaker speech probability. But this model is not designed for overlapping speech detection because it was trained on concatenated utterances. Our first target speaker VAD model was very similar. We used MFC features and I vector speaker embeddings, three-layer BLSTM with projections, and three classes of max layer. And outputs are the same. We used Kaldi ASR toolkit to train this model. Training utterances and I vectors were taken from CHIME6 baseline, and training targets were constructed from the forced alignment. Also for each utterance, we used its negative version with a random speaker's I vector, and the target speaker speech was replaced by non-target speaker speech in training labels. And after the training, we applied this model to detect each speaker's speech separately. But this led to poor performance, only 66% diarization error rate on the development data. We analyzed this error and found that it was due to high false alarm rate. And it was a consequence of independent processing. But we overcame this by introducing a mutual threshold. Considering a set of probabilities on the current frame, we found that if some speaker's probability is strongly dominated by the maximum speaker's probability, that it's likely no speech of that speaker on the frame. So we should to set it to 0. This figure illustrates this threshold. As you can see, for second and third speakers, the probabilities are very low comparing to the first speaker probability, so we set it to 0. And this simple trick provides dramatic reduction of diarization error rate, and we got 46% diarization error rate on the development data, and it looked promising. Next, we tried to improve this model by adding I vectors of 3 other speakers in this session as input. But this led to only a small improvement. And we tried to obtain TSVAD predictions from various permutations of these I vectors and average these predictions. But this was still not enough to get good results.
So Ivan, this is Sanjeev. Can I interrupt you with a quick question?
Yeah, okay.
So, in the previous slide, when you said that a lot of the false alarms, a lot of the errors were due to false alarms, I'm wondering what the nature of the errors are. Is it that the wrong speaker gets spuriously recognized in a few frames here and there? Or is it an entire chunk of the wrong speaker being recognized as the speaker? Because what you said over here, it's purely going by the probabilities. I was wondering if there is more information in the temporal sequence, which says that these are false alarms.
These false alarms were because if some speaker speaks, our system detects the speaker, okay, but in this time region, our model detects other speakers as well.
Yeah.
With lower probabilities, but still.
Is this wrong speaker there just for one frames, or is he there for all the frames of the?
No, it's for a frame sequence.
Okay, so it's just okay, got it. Okay, thanks.
Okay, so this model was not so good, and here is our next model, which predicts joint speech activities of 4 speakers, like END model. Here, speaker detection BLSTM block takes MFC features followed by 4-layer CNN and an I vector of one speaker, and produces SD hidden representation of the speaker. We do this for each speakers, and then we combine these SD representations by BLSTM layer. And outputs here are 4 binary classification layers. As we used Kaldi toolkit, it was easier for us to use 2-class softmax layers instead of sigmoids. So outputs here are 4 pairs of silence and speech probability. And training targets were constructed from forced alignment, including overlapping speech statistics from neighboring utterances. And note that negative training examples are no longer required for this model. To get better performance, we applied on-the-fly random permutation of speakers as described in this figure. We permuted both input I vectors and outputs in the same order. We also applied mix-up data augmentation technique. We added 800 hours voxel data with augmentation with artificial room impulse responses, but without creating overlapping examples. Also, mutual threshold was not helpful for this model because it detects joint speaker activities. And we got impressive 37.4 diarization error rate on the development data, but this with Oracle segmentation. And the question was, can we achieve similar results without using Oracle segmentation? We tried iterative estimation of I vectors. This idea is similar to Hitachi's recent paper from ASRU. We start from our best cluster in diarization system segments. We estimate I vectors on the segments, then we obtain TSVAD activities, and re-estimate I vectors on these activities, and so on. This process converged after only 2 iterations, and we got 38% diarization error rate, and this was almost as good as with Oracle I vectors. Okay, now about reliable I vectors estimation from TSVAD predictions. We used 2 thresholds to get reliable I vectors. First, we exclude low probability frames by an absolute threshold. If probability is low, we discard it. And second, to exclude possibly overlapping frames, we used a multi-speaker threshold. If probability for speaker I divided by sum of probabilities on the current frame is less than the threshold, we set it to 0. And this illustrated on this figure. First is absolute threshold, and second is multi-speaker threshold. And after this processing, we use these probabilities as per frame weights for calculating I vectors. Here is an overview of our diarization system in challenge. We used wide residual network X vectors with spectral clustering on cosine similarities. We got segments, estimate I vectors on these segments, and apply few iterations of Target-Speaker VAD. And after simple post-processing, we get final segments. The next important aspect is multi-channel processing. We tried WP deliberation, and this reduced the diarization error rate by 1%. Also, averaging of per-channel probabilities of TSVAD provided up to 2% diarization error rate reduction. But it was important to create a more sophisticated approach of using multi-channel signal. So we create the multi-channel TSVAD model. This model takes SD hidden representations from a set of channels. We used 10 channels here. And for each speaker combines these representations using a simple attention mechanism. And then attention outputs are combined by a BLSTM layer. And outputs here are the same as in previous model. Okay, for post-processing, we used a simple scheme consisting of median filtering, thresholding, combining short speech segments together, and combining speech segments separated by short pauses together, and deleting 2 short speech segments. And here are results for our TSVAD models with this simple post-processing. This is the first iteration of a single channel model, second iteration of a single channel model, second iteration with multi-channel model, and fusion of multi-channel and single channel models. And this improvement over the baseline is very high. We also tried an advanced post-processing approach based on multi-speaker Viterbi decoder. We used 11-state HMM, 1 state for silence, 4 states for each speaker, and 6 states for each pair of speakers. This model not consider 3 and 4 simultaneously speaking speakers because of low duration of such examples in our data. So TSVAD outputs are used as HMM emission probabilities, and transition probabilities are tunable parameters. We tied these transition probabilities for all states with the same number of speakers. So it was only 7 tunable parameters in this model: 1, 2, 3, 4, 5, 6, and 7. And these parameters were optimized on the development data to minimize diarization error rate. And after that, we applied Viterbi decoding to get most likely state sequence, and applied short silence and speech segments post-processing to get final segments. And this table presents results with Viterbi decoding compared to a simple post-processing scheme. Viterbi decoding gives lower diarization error rate, but higher Jakarta error rate. It's probably because this model not considers 3 and 4 speaker segments. Okay. Now let's move to the final part of my talk. And first, I would like to introduce new CHIME6 CALDI recipe, which includes TSVAD. This is a...
Let me interrupt you just for a second. Can you go back to the previous slide?
Yes.
The question in the Q&A, Manuel asks, is the attention over time or channels? I guess it's a few slides back. I hadn't seen the question earlier.
Here?
Yeah, so I guess this is where the question is. It says, is the attention over time or over channels?
It was attention over channels, not time.
Got it. Yep. Thanks. Thanks. Okay. Yep. Please continue.
Okay. Okay, our CHIME6 recipe. It uses baseline speaker activity detection, baseline X vectors. After that, spectral clustering. We estimate initial I vectors. We apply 3 iterations of TSVAD with iterative I vectors re-estimation. We apply simple post-processing, then guided source separation enhancement, and then ASR with the baseline TDNF model to get final recognition results. This recipe contains a pre-trained TSVAD model, as well as a training script for TSVAD. Now we are making a pull request to the Kaldi master, and I want to thank Dash, Ashish, and Finji for their help with this recipe. This table presents results of our recipe. You can see very significant improvement over the baseline. However, there is a performance gap between the recipe and our challenge diarization system, which is 6% diarization error rate on the evaluation data and 12% on the development data. The same for ASR results, significant improvement over the baseline, but 5% gap on evaluation data and 13% gap on the development data. Of course, this recipe is a compromise between simplicity and performance. And for the simplification, we did not include voxel data, multi-channel model, blockwise WP, mix-up augmentation and speaker permutations augmentation, Viterbi post-processing, soft activity-based guided source separation, and the most important, we did not include wide residual network X vectors. And testing this recipe, we faced a problem that TSVAD detects silence instead of one of speakers in session S09 in the development data. And after the analysis, we found the explanation. It's because weak initial diarization. So after first TSVAD iteration, we have too few frames for that speaker, and this leads to poor I vector estimation for that speaker. And with this meaningless I vector, next TSVAD iterations are not able to detect that speaker. But this can be partly alleviated by increasing number of frames for each speaker by reducing absolute threshold and multi-speaker threshold. So in challenge, we used multi-speaker threshold 0.8, and here we reduced it to 0 on the first iteration and to 0.5 on the second iteration. Okay, the next important question is, can we obtain better performance by using better speaker embeddings, for example, X vectors? We tried several versions of X vectors, and unfortunately, the better embeddings we took, the worse results we got. Why and how to make X vectors work in TSVAD? The first hypothesis is that X vectors are too high level, and it's hard to match X vectors with MFCC features in a simple network. Possible solutions are first, use more sophisticated network in TSVAD model, and second, add X vector extractor as a part of TSVAD model, as described in this figure. We already tried this in the challenge, but it was unsuccessful, probably because of lack of time. Okay, the second hypothesis is overfitting the small number of data and speakers. It was only 40 hours of training data and only 32 speakers. And possible solutions here are use strong regularization or just use more data. And the third hypothesis is that TSVAD uses not only speaker information in I vectors, but also other information, for example, information about acoustic environment. And here we can include this environment information to X vector embeddings, or we can combine X vectors together with other embeddings such as I vectors or R vectors. R vectors are the same X vectors, but trained to classify room impulse responses instead of speakers. Okay, the main limitation of TSVAD model is that it's designed for a specified number of speakers, for 4 speakers in CHAIM6. But how to extend it to an arbitrary number of speakers? Because it's necessary for applying in real-world applications. We propose this extension of this model. Given a set of n I vectors, we can compute n SD representations. Then we choose one as target, for example, first, and the others as overlapping. And overlapping SD representations can be combined by attention mechanism. And then after a BLSTMP layer, we have 2 output layers. Target output layer for our target speaker and output layer for overlapping speech. And this model in theory can detect any number of speakers, but it still requires initialization. And the number of speakers can be reduced on iterations of TSVAD, but cannot be increased. So if we have low probabilities for some speaker, we can discard the speaker for next iterations. But we haven't tried this extension yet. And we think this should work at least if we have some audio examples enrollments for each speaker. The other interesting directions are improving network architectures in TSVAD, for example, replacing BLSTM with self-attention network. Advanced multi-channel processing, for example, joint training of beamforming and TSVAD model. And of course, it's interesting to try TSVAD in the other tasks, such as AMI and LibreCSS. Okay, that's all. Thank you for your attention, and I'm ready to answer your questions.
Ivan, that was excellent. Thank you. So as promised, Ivan kept his talk short. We have plenty of time for questions. The audience, if you could please raise your hands, I will allow you to speak one by one and you can ask your questions. The first hand is already up. It's Chenglin Chu, so I'll say allowed to talk and hopefully you can speak now. Go ahead.
Hi, Ivan, nice. Thank you for a nice talk. Actually, I'm interested in the Target-Speaker VAD. So for this part, I saw your output. So it's the extraction of the speech or the just giving the time labels for the Z speaker. Do you estimate the speech for the target speak? It's like the speaker extraction. We want to get the voice of the target speak. We always only output the target speak.
Oh, I'm sorry, I can't get your question. Could you repeat?
Okay. I mean, is the output is like a VAD label, or it's the speech of the target speaker?
Oh, the output of the TSV. I think each speaker has 2 outputs, the probability of speech and silence, and there are 4 such outputs.
Yeah.
Is that right, Ivan?
For example, page 23.
Yes.
Yeah.
So for each speaker, we have 2 probabilities, probability of speech and probability of silence.
Okay, but if you like this, for the overlap part, you don't do the discrimination of the different speaker, right?
These probabilities are sum to 1 for each speaker.
For example, for the overlap part of speaker 1 and the speaker 2, so you output
yes.
speech label to output 1, also to output 2.
Yes, we will have a speech label, high speech probabilities in both outputs. Yes.
Yes, but in this case you don't separate the speech, right? When you use this label to do the duration, then the speech part is still overlapped, right?
Yes, we don't extract speech. We just detect speech. We don't get audio files with separated speech.
Okay.
Yeah, in the chime system, I think their ASR is a speaker bias ASR, so they have this profile, so they can their ASR should have the capability of handling the overlap speech, or after this they have a speech extraction. So the speaker overlap is hand afterward, I think.
We used guided source separation to extract speech of each overlapping speakers.
Okay, understand. Actually, we have a work in industry 29. Then we do the speaker extraction for multi-talk speaker verification. So we check the speech of the target speaker, then we do the verification. So I think it's a similar idea can be used for the duration. Then we can just check the speech of the target speaker, then we do the duration, right?
Okay. So Chenglin, I think your question was answered adequately. Should we move on?
Oh, sorry.
Was your question answered adequately? Should we move on?
Oh, yeah.
Okay,
yeah.
Sure. Okay, thanks. Yiming had the next question. Yiming, go ahead. Yiming, you should turn on your microphone. You're still muted.
Sorry, I have no questions. I just click the wrong button.
I see. Okay. All right. No problem. Okay. Right. Zoe, do you have additional questions? Do you want to continue the discussion?
Yeah, so beforehand, actually, Paula sent some questions, and I think most of them is answered already in the talk. But there's one thing. So Paula asked, what happens if the clustering initialization stage is not very good? Is TS VAD able to convert to a good solution?
It's probably answered here. Here with not very good clustering diarization, but we still get a good solution.
Oh, I see. I see. Okay.
But it worse that it can be with good initialization.
I see.
And it's probably because of this problem.
I see.
Paula, go ahead. There's another question from Paula.
Yeah, so I just want to thank you for your great explanation. And I think all my questions were answered in your presentation. So I just wanted to say that. Thank you.
Okay.
Any additional questions from anyone? I know there are a lot of seasoned experts out there. I see Danny Garcia Romero. I see Martin, anyone who's been working on this problem for a while. I see lots of hands. Hold on a second. I'll need to get them in one by one. Okay, so Markui, I'm going to start you first. Go ahead, please. He's the one in the workshop who's been working on TSP.
Can you hear me?
Yes.
Yes.
Yeah, I'm very glad to ask a question. Actually, I'm working on the TSVD in the JSALT workshop, and there is one question. So when speaker numbers smaller than 4 in your structure, did you try to simply append the I vector with the other session speaker, like training set speaker, and test the result? For example, if the session the number of speaker is 2, did you try to append the like 26 speaker I vector to test the result?
Okay, do you mean can we use a 4-channel TSVAD model for 2 speaker recordings, right?
Yeah. Actually, I have tried on simulated set. It seems it also works, but I'm not sure it will work in the real test set. Yeah. Did you try it on the real test set?
We didn't try to use this TSVAD model for example, 2 speaker recordings, but I think it should work.
Yeah,
But
it works in the simulation test set, but I haven't tried it on the real test set. Yeah.
we didn't try it on simulated test sets.
Okay.
Only on real QIIME-6 data.
Okay. Thanks.
But if you want this model to work with such conditions, you can add fake I vectors in training. For example, you use 2 I vectors corresponding to real speakers and 2 fake I vectors, for example, 0 I vectors for the rest speakers. And this should help to work for a lower number of speakers.
Okay, I'll try it.
You're suggesting
Thanks.
that if you're trained with 4 speakers, but you know there are only 2, you should set the other 2 I vectors to 0.
It's possible, right? For example, you have a recording meeting of 4 people, but 2 of them just don't talk from the beginning to the end, and you have this. So it's possible to have this case. So that means 2 of them is not used at all.
Yeah, actually, we didn't have the other 2 avatars. So, if you want to test on the two speaker sessions, you need to get the other speaker avatars. Yeah.
Okay.
Yeah, that's all.
Yeah.
Yeah. Okay.
Yeah. Shinji,
Thanks a lot.
yeah. Shinji Watanabe, go ahead, please ask the question.
Okay. Thank you, Ivan. I'm Shinji. The very good talk. I have a question about a little bit similar to the Marquis the question, but in general, based on our experience in the E&D system and so on, this discriminative diarization approach is working quite well if that we have the kind of a matched condition. In your cases, you actually have the 40 hours of the time training data. So then apply to the dev and eval set. And I would say that you have a kind of some enough amount of matched training data. Matched here means in terms of the overlap ratio or the loom impulse response and so on. So I would like to ask whether you have some experience of applying this kind of approach to the mismatched condition. Again, the E&D system and so on. For us, the most important part is how to create the mixture, overlapped mixture, matching to our application. So could you have some comment or answer to my questions?
Yes, actually, we didn't try to apply this model in mismatching conditions, but we tried to train EEND model on voxel data, and this model was much worse than EEND trained on QIIME data.
Exactly, that's what we often observe. So I think similar things may happen to your model. So I'm very glad to see if in your future, you also tackle the mismatched problem and see some progress. Thank you so much.
Thank you.
I'm sure we'll try it, Shinji. Yeah, thanks. So Shinji, you can stay on if you like.
Sure.
I think there is a question from Alexander Zakornitsky.
Hello, everyone. Hello.
Hello.
Thank you for great presentation. I have a question. Let's say I want to implement your approach in streaming fashion. Do you see some major obstacles on this for these tasks? Thank you.
Yes, if you have to implement this in a streaming fashion, I think you need some enrollment for each speaker. And then it can work. Okay.
And do you think that latency will be relatively big because of I vector estimation, or it's something that can be solved?
Yeah, I think this problem can be solved, yes.
Thank you.
Online, you can also use the recursive updating style of stuff, right? Once you get in the middle, then you already have the previous decision. You can update
Yeah, exactly.
Yeah, it has sense. Thank you. Thank you.
Thanks, Alex. Desh, you have a question? Go ahead, Desh Raj.
Yeah, so my first question was about like I think it has been answered already, but I'll still go ahead. So it's about the unknown number of speakers at test time. So say we have a lot of variability in the number of speakers in recordings at test time. For example, suppose it varies between 2 and 10. So for training, we can, I guess, train with 10 speakers. And if we don't have that many speakers in the training data, we can just add fake I vectors. But at test time, if we have trained with 10 speakers and we just have 2 speakers, I was wondering how it would affect, like, because that's a big difference between the train and test. So would it still affect it badly, or do you think it would do just as well?
Okay, I think for your case, you should use this extension,
Okay.
which allows any number of input I vectors.
Right. Okay, and my second question was, have you tried using TSVAD on already separated audio streams? So it wouldn't have overlap at all.
Oh, no, we didn't.
But since the method itself does not really rely on like I guess it can be like easily applied to separated streams, and then since we know the identity of the speaker, we can just match it across streams, I suppose, right? Because one of the things that in JSALT that we're working on is applying the diarization and recognition pipeline to separated audio streams. So I was interested in seeing if we can use TSVAD with separated streams as well.
Any thoughts on that, either Ivan or Zoe?
Oh yeah, I mean, I just agree with Dash. Yeah, we are actually having some exploration. Say how do we want, because the question of handling the long sequence is for example, we have 3 components: separation, diarization, and recognition. How to arrange them, because any module could be benefit the other one. So how to arrange them, or iterative one, is actually one thing that's very interesting that being explored. So I think, yeah, that's just the questions on this perspective. So if
Yes,
we have a separation, yeah.
I think the best way is to train all these components jointly.
Yeah, eventually, I think, yeah, I agree. But eventually, right.
That's one of our the topic in the JSALT, right, Joe?
Yeah, exactly, yes.
Okay. There's another question from Sunit Sankaran. Sunit, go ahead.
Can you hear me? Hello?
Yep.
Yes, okay, cool. Thanks, Sven, for the excellent talk. I learned a lot. Thank you for that. I have one question in the multi-channel TS VAD. If you can go to the slide, please.
This one.
Yes. So I remember you said N is 10, right? You use 10 channels eventually to obtain the TS VAD results. And if my understanding is right, you will have to eventually use channels across devices as well. So did you have to do anything particular to sync up the devices before using?
Could you repeat, please?
Sorry. So what I wanted to ask was, since the channels are spread across multiple Kinect devices and they're not synced, do you have to do anything particular to sync up the devices?
These devices were synchronized by array synchronization script in CHAIM6 recipe.
As part of the recipe itself, okay.
Yes, synchronization is important here.
Right, okay, yeah, sure, thanks.
So Sumit, I think you're right that the data wasn't recorded synchronously.
Right.
The chime organizers made a very good effort to try and synchronize it to the extent they could. I don't know if you can still guarantee frame level synchronization, particularly at the 16 kilohertz sampling rate. I don't think that's true, but it's close enough.
Mm-hmm. Yes, in fact, that's one thing which I mean, when we worked on Chime 5, that's one issue which we had. And yeah, it's good that we had some kind of fix for this for Chime 6. That been had otherwise.
Shinji, do you want to say a little bit about how the synchronization was done?
Yes, we actually have another microphone, which is kind of well synchronized. So we try to kind of use this one as a target, and we'll kind of shift the original microphone, the signal. And all the kind of code is also released the chime, the challenge part of the kind of script. So if you want to know more about the details and the implementations, it's included in the chime recipe as well. So you can check it.
Thank you. Thank you.
There is one more question from Hakan. Let me allow him to talk. Hakan, go ahead.
Yes. Yeah, I just wanted to ask how you use the mix-up training. Maybe can you give a little more detail? When you mix up two examples, do they have to come from same set of 4 speakers? But if they come from different, how does it work? Or yeah, could you explain more about that?
We tried several versions of mix-up. We tried to mix only input features, but not I-vectors and not labels. We tried to do the opposite, and all these options are performed okay. So as far as I remember, finally we mixed all. We mixed input features, we mixed I-vectors. So we took 4 I-vectors from one example and 4 I-vectors for the second example and mixed them together. And the same for outputs. So we got soft labels.
So they didn't have to be same speakers. They can come from any training example.
Exactly.
Okay, interesting. Okay, thank you.
I have a quick question. So for this diagram, you have the IVEC1 to IVEC4. So you share weight, then you can get SD1 to SD4. But you combine them together. How can you measure guaranteeing the output one is speaker 1? Does they have some speaker permutation problem here?
No, there is no speaker permutation problem because our I-vector position matches with our output labels position.
But the last layer is combining all the SD1 to SD4 together. Then
Yes,
to the
but
prediction.
this is concatenation. This is not sum. So this BLSTM knows positions of these vectors.
Okay. Okay. Thank you.
I think Manuel had a question. Manuel, go ahead.
Thanks, and thank you a lot for the presentation. I have a follow-up question on mix-up. When you say that you mix the labels, in the original mix-up, they say 0.5 label 1 plus 0.5 label 2. But in speech, if you have 2 speakers, even if they are multiplied by half, both of them are still 100% present. So do you have the labels be twice 0.5, or you have 2 ones? I mean, both speakers are completely present.
Oh, we used a very small mix-up rate here, about from 0 to 0.3, as far as I remember.
Yeah, no, but Ivan, I think Manuel's question is the target one for both speakers, or is it half and half?
It's one for both speakers.
Okay, thank you. Because yeah.
But we had one main speaker and one additional speaker with small weight.
Okay, thank you. And maybe I can have a second question.
Yes, please.
Yes.
So now on this slide, exactly, you said that the BLSTM looks at the SD1, SD2 in sequence, and that the BLSTM is aware of the position.
Yes, BLSTM is aware of the positions.
But so there is a implicit order of speakers on the sequence. So having SD1, SD2, SD3 is not the same as when you permute them inside of the input features, input sequence, or is it the same? Maybe I misunderstand something.
Do you mean our on-the-fly permutation or not?
For example, yes. So with on-the-fly permutation, because the order is changing, the output will also change because of the neighbors.
Yes, outputs are changing. Yes.
Okay. Okay, thank you. Thanks.
So Ivan, if I understood you correctly, the lower part where the I vectors are and the output of the speaker detection, the middle layer, and the final outputs, all those are permutable. And the BLSTM is the only one which thinks in terms of order. And that's why you're permuting the rest so that it knows not to worry about the order, that it tries to get an order invariant. It tries to match the corresponding input in the output.
Yes, exactly.
Hakan has one more question. So sorry, Hakan, I should have not removed you. Please ask the question.
No, it's okay. Yeah, I was thinking about the training procedure. What was the length of the blocks that you trained from? And did you take care of a certain spatial overlap structure while training? Or it was just totally random overlap between these four speakers when you were training your model? Like when you use, for example, voxelab data, how do you mix them? How did you mix them?
Okay, for the voxelab data, we just used a single speaker data for training.
Oh, you didn't mix. Okay.
We didn't make artificial overlappings in these examples.
Oh, you always use real. Okay, either single speaker, or when it was Chime 6 data, I guess it was already real overlapping training data.
Only real overlappings, and for the training we split our utterances to 40 frames chunks, and we use 30 frames left context and right context for our BLSTM training. So it was
okay.
very short chunks.
Okay, so just to verify, you never trained from artificially mixed data. You always used
yes,
real.
exactly.
Okay, thank you.
Ivan, I had a high-level question. If I wanted to, a lot of the things in this TS-VAD view of looking at problems is a little bit of an offline processing model. So what do you think, where can this go if I wanted to do online processing, like some kind of streaming processing? With the E and D things that Shinji and Albert talked about earlier, it had at least this slight flavor of being able to go left to right in the recording. Do you have thoughts on how much of this can be made left to right?
Yes, for streaming applications, first we need initial I vectors for each speaker, and then we can re-estimate I vectors using left part of our sound.
Okay. But the initial one will be the tough one, where to get them before you know.
Yes, for initial, we need, for example, some pre-recorded audio for each speaker.
Okay. Right, anyone from the audience or anyone else on the panel, any last few questions?
I can ask one more question about the ground truth targets for the diarization. So have you played with anything in the ground truth targets, or how did you obtain, first of all, the ground truth targets? Is it just based on energy, or is there any other way? Can you comment on that? Yeah.
Yes. We took training data for acoustic model, training utterances, and we had forced alignment phone level. So we converted this phone level alignment to training targets for our model.
Okay, in the overlapping case also?
Yes, for the overlapping case, we took neighboring utterances and took overlapping targets from these utterances. And this is implemented in new culture recipe, so you can check it.
Okay, thank you.
All right, that was a very nice discussion. We can take one more or last question if anybody has one, or maybe Zoe, you get the last question if you want.
Yeah, I think, do you think it would be helpful if you don't mix them? I mean, for example, for VoxLab, you can concatenate them, right? Would that be helpful? Because this is what we have is a BRSTM model, right? So would that be, because if you only train with one speaker, this model never actually sees the speaker change and something behavior like a turn taking, right? Would that be, do you think it would be better, helpful? Or?
Yes, it's a good idea, I think.
I see. So you didn't try, you're just trying on individual VoxLab
Yes,
data set.
we didn't try for the simplicity.
I see.
Because
I see.
it was a challenge, deadlines, and so on.
I see. Understand. All right.
Deadline, channel limitation of what data you can use. Yes. All right. Okay. Great.
Cool.
So Ivan, we are past the 11 o'clock hour, but thank you very much. This was both an excellent talk and a very useful discussion. So again, everybody, let's give Ivan a big hand. Let's call this plenary talk to a close, and workshop participants, we meet again on Monday, Monday to do our weekly update. And then next Friday, we have plenary talk, right?
Have a nice weekend.
Everybody have a good weekend. Ivan, thank you once again. This was really excellent.
Thank you. Thank you, Ivan.
Thank you. Goodbye.
Bye.
Bye. Thanks.